question about like asymptotic notation. So here we have proved that the square root of the n plus 100 is like big theta square root of n. So does anybody have any idea how to solve this one? What is the approach? How do you solve this kind of question? I briefly...
You have to find two C's that satisfy the definition of...
Yes, exactly. You can do limits too, but for limits, just so you need to find a limit and show that this is the case, and then find, okay, it's equal to 0.
Seems like unnecessary work.
Yeah, there are two ways to just prove it, but eventually you can do any of them. But first of all, one of the way, if you have it in the like final exam or something like that, if I give you this question, how do you solve it? That's the way that you need to do. So first of all, you need to look at the question and see what is that. So let's see. I have big theta. It means that for big theta, just prove it. We must find two things. Okay, let's go back here and write the solution. What is that? We must find three numbers because theta has three positive numbers. One of them is C1, another is C2, and we have N0, such that, okay, so now we need to write the equation that we do have for big theta. How do you write it? When you write it? Anybody? What is the definition of big theta?
You got G, C1, G of X.
G1 is this one. So, okay, C1G, which is this one, okay.
And then less than greater than f of X, which is the other one.
Yes, that's correct. And how about?
And then less than greater than again.
C2.
Yeah, C2.
Yeah. And then you should show it's greater than 0. For what? We need to show it for all n.
For all n more than n not.
Yes, exactly. Okay. What I'm gonna say, okay, let's see if I can do something. Let's think that I'm saying, okay, if C1 equal to some, I don't know, let's consider C1 to be 1.
We could do C1 1 and C2 is be 10.
10? Number 10?
And not to be 0.
What do you mean? And not should be greater than 0?
Sure.
Okay.
And C2 could be 10.
Okay, let's try it out. C2 to be 10 and then and not equal to 0?
Yep.
Okay. Then how do you write it? You say for n greater than n not. How do we define it?
Do we just plug it into our definition above?
Okay, so but how do you show it? It's a proof. You need to prove it. So if I put it here, so how can I prove it? I can check it out. For example,
I guess you could split the inequality up.
So let's see. Okay, so we say I put this one n plus 100 less than 10 of these. And then what else do you want to do? It's become 100. This is not gonna work because let's show you. I can do this one. This is gonna be and then I can show this is all overall, sorry. This overall should be, let's write it. This is gonna be this one. This is gonna be less than 100. To just remove this one and it shows that n is less than 0, which is not gonna be this one because you say n naught is gonna be 0. So what does it show? It shows that n naught should be greater than 0, and here you prove that n naught should be less than 0. These values doesn't work. Does it make sense? You cannot choose any number. Is it clear?
Wouldn't it be n now is less, like n plus 100 is less than or equal to 100n?
Oh yeah. Sorry. Yeah, you're right. Okay, less than n. Okay. And yes, let's see. Sorry, you're right. So it's become 99n greater than 100. It means n greater than 100 over 99. So still, it has issues, you know. We said here n should be greater than 100 over 99, and you just say here for all n greater than 0, which is not gonna work. Because most of
Oh,
the,
so
when you say
could we
this
just change our n to be like higher, or like be like 2 or whatever?
to be 2, yeah, but you know, you need to consider the way just putting number is not a great way to do that. You need to have a strategy to solve these things, you know. Yeah, you just now you want this one, and then what else you need to say? Just n greater than minus 100 for sure, which is this is nothing. It's okay. And then how about the next one? Okay, let's see. What do you have? So we do have the next one, which is gonna be, so what was the C1 considering? We need to consider C1 equal to 1. This one less than what? Less than and again. It's gonna be n plus 100. This is gonna be work all the time. If you consider C equal to 1, it's gonna work all the time. That's okay. Yeah, you can consider this one. N greater than 2, C1 and C2 equal to 10. Does it make sense?
Yeah.
Yeah, there is one way. Let me clean it up, just having it here, because I'm gonna force this one. So, and then I will show another way to do that. That's one way to do it. Okay, here this one should be 2. We have this one, and then so I did everything right here. So here, okay. Let me write it. Oh, I'm so sorry. 99, which is gonna be n greater than 100 over 99. And then this is working. If I consider this one, and this is working too. Okay, we're sure this is working. But let's do another way. That's the one of the things we realize. It means that we can consider different ways to prove it, different numbers. There are so many things in chat. Let me see. Yeah, we can do that. So let's see them. Okay, for the homework, you have a question about the homework. Let's talk about that at the end of the class. So, okay. Yeah, you can use limits. So let's do other thing. Let's see if I just choose different numbers. Okay, let's see if I consider C1 equal to 1 again, C2 equal to this, and N naught equal to 10. Then what do I have? Let's see. If N greater than N naught, what do we have? Let's do some way to do that. I say, okay, first of all, I know N is greater than 10. And if this is the case, what else? And I know that minus 10 is less than 0. That's obvious. Am I right? Does anybody have any question?
No.
Okay, this is obvious because there's nothing wrong here. So let's do something. I say I want to show this equation. What should I do? So let's do it. Let's say, okay, here I do have this one. Probably just give me one moment. I just need more space because I need to put all of them in one page. Less than 0 and less than n. Here, what I'm gonna do, I put 10 here. I need to make that equation work because here I put, and actually we do have 100 here. So yeah, this is gonna be n equal greater than 100. So this should be 100 and this should be 100. So I do have 100 here. So what I'm gonna do, I say, okay, n is equal to 2 minus 1n. So this is equal the same because if I do 2 minus n, it's gonna be n. And here what I'm gonna do, I say minus 100 is less than, this is 0. 0 means 1 minus 1n because this is exact same thing. It's gonna be 0. And then let's continue. Let's do and here. Let's do and here too to make it easy. Okay, let's keep going. So what I'm gonna do here, so I can consider this one to be C2, but C2 is a square. So it's gonna be minus 1n. This is gonna be 100. Let's do this one here too. A second minus 100. This is gonna be 1 minus C1 squared. And I'm trying to make that equation. So here, let's put and here. So now let's keep going from here. So what's going to happen here? Let's do it here. So if this is 100, so I put so I put 100 here. Bring n this side, is become plus n, less than equal C2 squared n. So that's what I want. So this is the first part, and here what I want is gonna be, let's bring 100 this side. It's gonna be n plus 100. This one is gonna be C squared n because I bring it this side. And let's move them. Now, if I do the square root, so what's going to happen? So this way is gonna be, I do have two things. Look at this one. If I keep going, here I do have 100 plus n. It's gonna be C to here, and then this way it's gonna be C1 n plus 100. So then based on all of these things, what I'm gonna have, I have C1 n. That was the C to n. This is this part, which is gonna be greater than 0 because n is positive, this one is positive. This is less than n plus 100, and this one shows this is gonna be this one. I put these two together. So this is gonna be this, and this is gonna show this one C1 and n plus 100 C2. So we proved it. Does it make sense? Okay. So it makes sense, am I right?
Yeah.
Okay, so let's keep going. Let's learn about the theorem. So we finished our problem. So let's talk about another theorem. What I'm gonna say if h of n is big O of g of n, and I show if I know that f of n is less than equal to h of n for all significantly large n. It means it doesn't mean that being for small n, for large n, then what's going to happen? Then I can say f of n is big O of g of n too. So it means that I know h of n, which is going to be a function big O of g of n. And then I know another function is less than equal to h of n for big N, large N. And then I can show, oh, f of n is less than, f of n is big O of g of n too. This is helpful, actually. Some of the problem that you can solve with this one, actually. But anybody know how to prove it? How it works? Why it's working? Tell me how it works. Everything comes, when I'm trying to solve this thing, everything comes from hypothesis. That what is the definition? Let's go back to definition. By the hypothesis, here, what do we have? First of all, I need to show this one, this part. I need to use this one. This one, what does that mean? When I say h of n is big O notation of g of n, it means there exists positive C1 and N1 such that, this is the definition, for all n greater than N1, what I'm gonna have? I'm gonna have h of n greater than 0, less than C1 Gn. This is the definition. I know this one. This is the definition of big O of g of n. And then I do have the second one. So what I do have, this is another, it's the if f of n less than g of n. So let's use that one. What is that shows? This is one bullet point. The second one said there exists positive number n2 such that for n greater than n2, what I'm gonna have? I'm gonna have, because this is, we say it's less than, so f of n is greater than 0, and then is less than h of n. In this class, you consider all of the f of n, as I explained earlier, is going to be asymptotic, non-negative values. So it means that this is going to be hold all the time. This is the blanket assumption that we have in the past. So I have it in another class, blanket assumption. We know that f of n is asymptotically non-negative. This is a definition we already know. Okay, now we do have this one. So we do have two. We have two. This is the first thing. They're all coming from the definition of the theorem. So this is this one and this one. And we want to show that this is Hall hold. How do we show this one? Let's go here. So I already showed this one. I already showed that this is the two. What I'm going to show, when I'm talking, I know this is going to be whole based on the definition. What I need to show when I just prove it, this is going to work for your homework too. You use what we have in the question and prove what you need. For proving, we should show that there exists C2 and not positive numbers such that for all n greater than n naught. So go to definition. We want this one. What does that mean? F of n of equal to big O of g of n. It means what happens? So let's see. When it shows this one, it means we need to prove this one. We need to prove f of n less than C2 g of n. This is the proof. That's what we want based on the definition. But let's see how we can do that. So I know these things. I know to show this one. We can see this one. F of n, we need to combine these two equations together. So how do you say this one? Okay, I say I need to show that one. I'm saying, okay, let's consider C2 equal to C1. It means this C1 and this C2 is equal because I have this one, C1 g of n. So let's consider this one. And n naught is going to be the maximum of n1 and n2. Why? I will explain why. Because look at this equation. I know the second one. I know this is hold for n greater than n2. So I know that f of n is greater than 0, less than h of n. I already know that. This is coming by 2. Then by 1, what I have, let's go here. What I have by 1, it says that h of n less than c of g of n. So I can use that one. So I can say, okay, this one is already, h of n is already less than equal c of n g of n. So I already know that. So just consider c1 and c2 is equal. So it's going to be c2 of g of n. So what do I have here? Is I have 0 f of n less than c2 g of n. So that's what I need. I need to show this one by what I needed. But why do I need this one to be maximum? Because it may need to show that both second and equation one both hold. It means you need to consider the biggest number. So from that one onwards, so it's gonna hold. So you show this one, it's done. It's done. So it means that you proved it already. Does it make sense? Anybody has any other question? Okay, you got it. So let's go back. Let's show another theorem. These theorems are proof. It means you can use it for solving the homework if it's a theorem. So the other theorem that we have, I know if you can use them for proving other than that. So I know that h of n is big omega of g of n. And what else? I know that f of n is greater than equal to h of n for all significant large n, then f of n is going to be big O omega of g of n. This is the other one. You need to prove, you can prove this one. Just solve it as the exercise. So this is going to be your, consider this one. I have two parts. This is going to be for next quiz actually. So this one of them, you need to prove this one. This is for next quiz, and I do have another one for tomorrow. So, okay, this is the next one. If h of n is big omega of g of n, and h of 2 of n is gonna be big O of g of n, and what we have, h1 n less than f of n, and this one less than h2 of n. This is gonna be part of the quiz for tomorrow. Okay, this is gonna be this one. We say for all significantly large n, then what we are gonna have? Then we can send f of n is big theta of g of n. Based on the proof I showed already above, try to solve these two for tomorrow. So you have time to tomorrow to prove it for the homework, for the quiz. So you can write it as like a note, I don't know, in the paper, or you can type it out in Word, LaTeX, anything. So, but just, it's already easy. So just go through it and let's just solve it. So I do already have, I will post it after the class this part. And then based on that, you can prove this too. Does it make sense?
Can you go up really quick so I can see the other one?
Yeah, I will post this one actually. I will post this notes right now after the class. Okay, sounds good. Okay, let's solve another. All of these things I'm solving here, just trying to help you guys understand how to solve the homework and get ready for final exam and then like midterm, because this is going to be part of the final exam too. So both midterm and final exam. So okay, let's go back. I'm going to solve another example. Let's solve this example. I want to prove this one. Let's see. Prove that. What do you want to prove? I saw that let's consider k is greater than 0 and prove that by, let's the other way. Let's write it like this. Let k greater than 0, prove that. What do you want to prove? The summation of I from 1 to k, ik is big theta of nk plus 1. Does anybody know how to solve it? Do you want to prove this one? Any idea? So let's look at this one. I want to prove theta. For proving theta, I can do two things. If I prove O, big O, first I prove big O, and then also I can prove big omega. I can prove both of them. If I prove this one and this one, I already proved big theta. I just need to prove this one. Yes, correct. So how do we do that? Observe. We have this one. We say the summation. I want to prove this one, the first one. Look at I from 1 to k. Ik. K is a number less than n. So if this is the case, if I do summation up to 10, this is the positive number. And then if I do summation up to 100, summation of numbers up to 100 is going to be bigger than summation up to 10. So this is going to be less than I from 1 to n, and then put n. Here, this is going to be I. Yes, this is going to be n, nk. So because this is, instead of putting I, which is going to be a smaller number, let's consider the biggest number, which is going to be n. So this is less than this number. So what's going to happen to this term? This term is going to be this summation. This is going to be n, nk, because this number is going to be a constant from 1 to n, and this is going to be the summation. So this is going to be nk plus 1. And we already show is less than this number. So this is going to be, if it's less than this number, it's going to be big O of n k plus 1. We just need to consider c equal to 1. Because you say, okay, what I showed, let me write it here, maybe make it easier for you guys to understand. So I said summation of I to k, ik is less than nk plus 1, which this is going to be c equal to 1. So this is going to show that ik is big O of nk plus 1. Does it make sense? I show this one, this part. I show the big O. Why I use this summation? Why I use then nk? Because I want to reach to this point. I need to know, because I want to reach to this point, I need to consider some way to just get that point. Does it make sense? Now for showing the big omega, I need to find a lower bound. Let's do something like this. Let's take also. So we need to show the other way. I need to show this one is greater than equal some positive number c and nk plus 1. That is the purpose. I need to show this one. That's the purpose, yeah? Because I want to show big omega. So I need to find this equation. How do I find that? I say I know this based on what I write here. This summation, consider this one AK. If it's a start from 1 to K, it's going to be bigger than a starting. It is going to be bigger than a starting. Something in the middle. Instead of starting from 1, for example, starting from something in the middle, so it's going to be I equal to like floor of n over 2. It means the biggest number. If I divide, it means if I do summation from 1 to 10, it's going to be greater than summation from 1 to 5. So I just put this one. This is going to be greater. So, and then if that's the case, what's going to happen? So this is going to be number n. So from this one, so what I'm going to do, I'm going to consider this summation. This one is going to be I greater than, because for anything, if this is the case, for anything I greater, if I consider I plus this one, it's going to be, this value is less than this because I consider n over 2, 2. If I remove that one, I guess that for every n greater than this one, this is going to be the case. So it's going to be this one to n, and this is going to be n over 2k. Why? Because every I is going to be greater than this number. It means this summation for sure is going to be greater than this summation because I just considered the smallest number here. So, and then what else I'm going to do from here? I said, okay, this summation based on the definition is going to be, because I consider this way, and this is going to be n, it's going to be n over 2, because there is no, it's going to be this one plus 1, which is going to be floor, n over 2k. This is the floor. The ceiling, sorry. It's going to be, sorry, ceiling. So, and this is going to be what? This equation, n minus floor is equal to n over ceiling. This is sum of the mass, and then plus 1 over n over 2k. There are two things you need to remember. Since there's some rules. First of all, n over 2 floor plus ceiling is all the time equal to n. This is the equation. You need to use this one in future too. So that's what I use here. It's like n minus this one because I bring here and this is equal to this one. So that's what one of the things. And the other things, you know that if I have floor is greater than x minus 1 and ceiling is gonna be greater than x. This is another definition for sure. These two is some of the things that you need to remember all the time for solving this kind of question. Okay. So let's go back. And now I did this one. So based on this, I say, okay, if I know ceiling floor is greater than x minus 1, so I can remove this floor and put this is gonna be greater. Instead of this one, put n over 2 minus 1 because this is the equation, minus 1 plus 1. And then instead of floor, instead of ceiling is greater than x. So I can remove the ceiling. So it's gonna be n over 2 to the k. So I already did this one. This is gonna be n over 2. This is gonna be n over 2k. So this is gonna be is equal n over 2 k plus 1. So what I can do, I can bring 1 over 2 out and put this one n k plus 1. I want to show this one, am I right? I want to show n plus. I need to find C2. So that's C2. I consider this one to be C2. So then I show that this is going to be big omega nk plus 1. Is it clear? So we have this equation trying to show this is going to hold. And now I show two things. I show this is a big O, and I show this is the big omega. So what we can conclude If we show both of them, we can conclude that ISK to IK is equal to big theta NK plus. For any question, so anything in the homework, anything in final exam, if they ask about big theta, you need to show two things. You need to show that big omega and big O's exist. If they are exist at the same time, so what you can show, it's already proved. Does it make sense? One more thing I need to fix. This is N. Yeah, this is N. Here it should be, this is gonna be, let's fix this one. This is N. This is N, and this is N2. This is N. N, and then this is. Okay. So, anybody has any other questions? So, and this was N, this was N, and this is N, and everything is correct. Okay. This is N. Does it make sense? Any questions so far? Okay, there is something really important you can use in future. So, okay. We do have this. Let me write it here with another color, actually. Maybe yellow. So we do have this is consistent with. What is this consistent? That was the proof of, that was what I showed here. What it was consistent about. I think probably you saw this one. We say summation of I from 1 to ni is going to be n plus 1 divided by 2. Probably it's reading in your math, which is going to be big theta of n squared. You see, like here, this summation 1 to n I k, k is 1. It means it's going to be n plus 2. So this is the first one. And then let's consider I to n, I squared. And then if you see in the past, in the math class, this is equal to this one. Oh, sorry, this is going to be 2n. This is going to be 2n plus 6. Okay, this is going to be, consider this value. So this is going to be theta of n and cube, because 1, 2, 3. This is going to be n cube. And that's what we showed. We showed the summation of I from 1 to n. I k is going to be theta of, or yeah, theta of n k plus 1. But what also we can show? We can show summation of 1 from 1 to n theta of I is equal to theta n squared. This is what we can show. This is the exercise. Let me write this one as another exercise. You need to prove it yourself. So, okay. Exercise. If I have this one, theta of I is equal to theta n squared. And then you need to show this one. Does anybody know what does that mean? What does this mean when I consider here? What does this mean actually? When I say theta of I, what does that mean? So when I say theta I, it means it's here, theta I stands for a fixed function. It means that f of I is equal to theta I. So it means that I'm gonna show the summation of 1 I to n, f of I is equal to theta n squared. That's what you need to show. Does it make sense? Try to show this one. If you have any question, you can reach out to me and we can talk about that. Okay. Let's go, and I explain about big O, big omega, big theta, small o, small omega. We talk about definition of the small omega, big omega, small o, big O, and then some of the things that we showed. So we proved that we show the limits, some of the, like, let's put some note here. So let's go back and write some of the notes actually. So first of all, we say that small omega of g of n is in the subset of big omega of g of n. We show that one. We plot that whole like Venn diagram. So we already showed this one. So this is one of the things we need to remember. So, and then let's try something else. So I showed you guys something the other day. I just explained the analogy of like big O is like less than equal, big theta is like greater than equal, theta is like equal, a small omega is less than, and big omega is greater than. So we talk about this analogy actually. So, and then I think I show a few problem that we solve. Let's see what we can try, and then let's go. Does anybody have any question up to now? No question. Okay, sounds good. So okay, so let's see if I can solve any other question. Let's solve this one. Let's solve this question actually. It's a nice question. So let's see. So I want to show that ln of n is equal to a small o of n. How do you show this one? How do you know how to define this? What was the definition of all of this when I defined it the other day? Anybody? We want to show this one. How we can approach it? There are two ways. One of them is finding C and not on the other. What was the other approach that everybody mentioned in the beginning of the class? What was the approach? Anybody is in the class actually? No idea? Yes, we can do limits. So let's go back and remind something. So let's put something as a reminder. What was the reminder? I just do the plot. So let's do a reminder. Okay, let's try to use this color. So we had a big. So I saw, okay, this is the first part. And I consider this part. I explained that here, L, we have a L, which is limit of f of n divided by g of n and goes to infinity. We say here L does not exist. So if L does not exist, it's gonna be here. Here L exists. So here it's gonna be divided to a few parts by itself. We say here, this part, this is gonna be big, a small O of G of n. So where? We explain that this is where L is equal to 0. Let's use another, which color? Okay, probably this color. Here, this part. Oh, let's do something better. Okay, let's use this one. This is where this part is L equal to infinity, which is gonna be a small omega of G of n. Here, this part I explained earlier, so this part in the middle, which L is between 0 and infinity, is where we have theta of G of n. And here is in the whole general, like this whole part, if there is exist or not exist, is gonna be big O of G of n. And this another part is gonna be omega of G of n. And then we have a bar here, exact same thing. Here, this part is gonna be theta of G of n too. So we are gonna have, if this is gonna be the whole omega O, and this is gonna be the whole omega, big omega, if the L exists and it's equal to 0, it's gonna be a small, and if it's gonna be equal to infinity, it's big, and in the middle is gonna be theta. So let's see, I know these things. What I'm gonna show a small O here. So if I wanna see a small O, what should I show? I need to prove that L is equal to 0. Does it make sense? If I show L is equal to 0, I'm done. Yeah. You can prove that, yeah, there is a small function, so f of n, and find the C and these things. Yes, that's correct. But yeah, that's a right way to do that. But there is another way to do it. Let's consider this one. Let's plot it actually and see it. Okay. If I do a plot based on the plot, this is gonna be n, because we consider function to be positive, because we don't consider a negative part. And this is the definition of the ln, so which is gonna be this one. So what's going to happen based on this definition, or based on this plot, and based on the definition, we say limit of L of n, which is gonna be f of n divided by g of n, which is gonna be n, ln. So this is gonna be ln of n goes to infinity. Based on this plot, what do you understand? When n goes to infinity, it means this n gets bigger and bigger, and this one gets a small. Ln is gonna be like, it's not gonna change that much. Based on the definition of the limit, as ln n goes to infinity equal to 1 over n, and this one is like, you remove this one, it's become n, and this is 1, so n go to infinity, so it's become limit of 1 over n goes to infinity is equal to 0. Actually, if you consider the growth, it means n grows faster than on ln. So probably everything, this is gonna be infinity before this part gets to infinity. So it's gonna be 1 over infinity, which is gonna be 0. You already show that because this limit of f of n divided by g of n and it goes to infinity is equal to 0. It shows that we have a small O of g of n. We just show this. F of n is equal to a small. Does it make sense? Clear? Okay. So we just need to show these things. So I do have more exercise. So this exercise is not it's a good exercise. Probably, maybe, you never know. Maybe they're gonna be in the final exam, midterm. One of them is this one. If I have ln of n, O n of nk, it's a big O for any k greater than 0. Or another exercise, ln of n, a small n of nk for any k greater than 0 and m is greater than 0, greater than equal. So, and then another one, let me go to the next page. So another one is gonna be E n, this is gonna be O of nk, a small o, for any k greater than 0, m greater than equal to 0, b greater than 1. You just need to prove that. It means find this limit. This is a small o2, all of them. Yeah, this is gonna be a small o. All of them is a small o. It means that just prove this is equal to, like, L is equal to 0. If you prove L is equal to 0, that's it, you're done. Does it make sense? Anybody has any question so far, or we are good to go? Okay, I'm gonna solve one more question, so which is really similar to what you have, one of the questions that you have in your homework. Let me solve that one too. So to give you an idea, let's see if I know I say f of n plus a small o of f of n. This is equal to theta of f of n. You need to prove this one. I know this is gonna hold. How do you prove it? Does anybody have any idea? How do you want to do that?
You probably use the definition of small o first.
Yeah, you can use a small o, or the other way, maybe makes it, if you don't want to prove, but if you want to find C1, C2, yes, you need to do big O and a big omega, and then you find theta. But if you wanted to use limits, the easier way needs to just show limit it between 0 and infinity. That's it. You need to show this one. Because if it's equal to 0, it means that, oh, this is a small o. If it's equal to infinity, it means it's big O. But if I show it's in the middle, it already shows. I just need to show it's in the middle. It's not 0, it's not infinity. So how can I show that? I say, let's consider this function, a small o of f of n, be equal to h of n. Actually, the other way. So I'm considering this one. Let h of n is a small o of f of n. And then what I'm gonna have? If you know this is hold, what is that gonna show you? What is this equation show you? I know this is a small o. What is a small o gonna tell me? It means if I have a small o, it means h of n divided by f of n, n goes to infinity, is equal to 0 for sure, because this is a definition. I have a small o. So that's it. Based on this small o, I know this one. So let's go back to the equation. F of n plus h of n. I want to show this one equal to theta of f of n. How do you do that? So I say, okay, it's going to f of n plus h of n divide by f of n. This is the limit. This is the definition if you want to show the theta. So this part is going to be the first part. The second part is going to be the other one. So n goes to infinity. This part is f of n. This part is g of n. F of n divided by g of n and go to infinity. F of n, if divided by f of n, is going to be 1. So limit 1 plus h of n divided by f of n and goes to infinity. What we show here, we show limit of h of n divided by f of n is already 0. So this is 0. And then what we are going to get? We are going to get 1. I know 1 is between 1 and infinity. 0 and infinity. I already show L is between 0 and infinity. So since I show that, I can say, okay, f of n plus h of n is big theta of f of n. I already showed that because L is between 0 and infinity. So that's the proof. That's one of the ways that you can show in the homework. Is it clear? Okay. Does anybody have any question? If not, just let rest for 5 minutes and then let's go back and finish what we started. Anybody has any question, or we can rest? Okay, so let's see, one more definition, and then probably we are gonna go to another part of the class. Okay. Let's have another definition actually. So we have another definition. What is that definition? We talk about big O notation, a small O, big omega, small omega. We say f of n is asymptotically equivalent to g of n. And what do we write? We write f of n is equivalent of g of n. And we say if and only if this limit is equal to 1. This is where we say that if this limit is between 0 and infinity, it means that this is going to be big theta. F of n is big theta of g of n. But we have another definition. If it's already equal to 1, we say this one is going to be like asymptotic equivalent. So it's still part of the big theta, but we say this part. Does it make sense? And then I showed something already, but let's write it here. This is like what we did. We said f of n, another, like with an example. We say f of n is equivalent to g of n if and only if. If and only if means it's both goes two way. If this is whole, this the other whole or the other way. So if f of n is equal to g of n, or let me write it better. So it means f of n is equivalent to g of n if and only if f of n is equal to g of n and a small o of g of n. So this is gonna be this one, but let's prove it again. Let's prove it. We say, okay, if I know f of n is equivalent of g of n, what I know if and only if this is happened, the limit of f of n divided by g of n goes to infinity. This is gonna be 1 for sure. I know that. So what I'm gonna do is say, okay, if I have this one, if and only if, so this is gonna be f of n, g of n minus 1. If I do the limit, so if I do this limit and goes to infinity, I just bring this one over here. This is gonna be equal to 0 for sure. And then what I'm gonna say, I just do these things, like a limit of f of n, I open it. So g of n minus g of n goes to infinity is equal to 0. So what does that mean? So this is gonna mean that this is the definition. This is gonna be f of n, this is gonna be g of n. So this is gonna be if and only if. What is that? It's gonna be f of n minus g of n is gonna be a small o of g of n. Because the limit is equal to 0, it means that's first part divided by second part is be a small o. So this is gonna show what it's gonna show. It's gonna show this f of n is equal to g of n plus a small o of g of n. So that makes it smaller. Does it make sense? Is it clear? You just need to show what you have. I know this is gonna hold. I need to show the other way. Is it clear? Okay, so I explained a few things in the. Okay, probably you got an idea about how it works. Let's see. Okay, Now we need to talk about another concept. We just done with like asymptotic notation. I'm gonna talk about another concept actually. So probably you guys see it in the past in another class. Does anybody know about induction? What is induction?
Proof by induction.
Yes. So do you guys have some idea about induction? I'm not sure where did you take a class on that before? So probably you guys have. Am I right?
Yeah, we had it in
Induction. Yeah, we have induction, like some of the things talking about induction. So let's talk about induction. So we need to know about induction because we use it in the class later for just proof and the other things. Let's go and talk about induction. We are done with asymptotic notation. Let's talk about induction. So, okay, let P of n be a propositional function. We can say, what does that mean? It means P is a function whose domain is the set of integers and codomain is the set of true or false. Is the set of true or false. This is induction. So we talk about a P of n be a positional function. So the domain is going to be set of integers and codomain is going to be set of true and false. How do you show that? So this is going to be P. If I want to define it, I say, okay, it's a start. The domain is a start from all positive integers and go all the way to true and false. That is the definition. This is means going to be subset 2, 3, or all the way, and then. So now I do have this one. This is going to be the P for induction, and I'm going to show this one how it works. So we need to prove induction. What is the question? So so it means that P is a sentence, a statement that who's true or false depends on the integer n. So what does that mean? So I want to put the meaning. It means that P of n is the sentences. It's going to be sentences, a statement, whose truths truths or false depends on integer n. So we need to do the induction for this one. So that's a mathematical method for proving a statement like that. Like what is the statement? So if I'm going to show the statement, it means that I'm going to show this one. This is going to be mathematical induction. Mathematical induction, which is going to talk about here, is a method for proving that for n greater than n naught, Pn is true. So for all n greater than n naught, Pn is true. Pn is going to be fixed integers. So Does anybody remember how the induction works? How it works? Do you remember anything from the past? How we define this induction?
You start with your base case, right?
Yes, we prove the base case. Suppose that I have, for example, example. Suppose we want to wish this one. We wish to prove. We want to prove this one. We use induction a lot here too. For all n greater than 1, I want to show that Pn is true. That's one of the things I want to show. Okay, let's see. Okay, I want to show this one. What is the steps? Okay, so we said to prove such a statement by mathematical induction. We perform actually 2 steps. Let's prove the first one. What is the first one? Let's see if I can change another color. Actually, something similar. Okay, what is the first step? As you guys told, it's gonna be base. What does the base mean? I'm gonna prove, for example, P here. It depends. If I start from 10, the base case is 10. But here my base case is 1. It starts from 1. I should show that prove that P1 is true. This is the base case. And then I need to do the second part, phase, which is going to be induction. What does induction say? It says prove for all n greater than 1, Pn shows that Pn plus 1 is true. This is we say this part. We said this part is gonna be induction hypothesis. So what do we say? How it works? So what we say, we say, okay, I start to show that it means if Pn is true, I can show that Pn plus 1 is true too. We are gonna prove that one. We assume that Pn is true, and we prove that Pn plus 1 is true too. That's the induction steps. So if I consider that the P based on this P1 is true, I can show that then Pn plus 1 is true too. So the other way, you can say based on if Pn minus 1 is true, Pn is true. You can just put n minus 1 here and Pn there. It doesn't matter. So that's the way we are gonna go. But let's consider solving this like this statement that I have here. Like P1 is for any n greater than 1, Pn is true. So how we would do that? First of all, we need to show the base case. What was the base case? Base case is like, I assume what? We assume that P, let's first of all, let's consider this one. Let's say n greater than 1 be chosen arbitrarily. And then we say assume, this is the assumption. We say Pn is true. And what we are gonna show? We show as a consequence Pn plus 1 is also true. This is the way induction works. You assume something and show the other way works. What we show actually, when these are done, what we conclude? We conclude if we show the base case and if you show Pn is true, and then show that Pn plus 1 is also true, what's going to happen? This is going to happen. We conclude that for all n greater than n, Pn is true for overall. So that's the proof. Let's like a domino. It's like a domino analogy. What does that mean? It means that you show 1, 2, 3, and go all the way n. I consider everything up to n is true. Then I show n plus 1 is true and the other way. So this is going to be for n plus 1. As I mentioned, there is a minor variation that doesn't start from n equal to 1. It shows that for all n greater than n naught, instead of 1, Pn. So first of all, what we are going to do, as I explained earlier, instead of proving for P0, we prove Pn and naught is true. And then for the second step, what I'm going to show, so I'm going to prove for all n greater than n0, if Pn true, I show Pn plus 1 is true. And that's it. That's done. You know, here the domino effect, it means that it's discarded from 1, but the other way, this is different. This one is to start from n naught. Or let's have another variation. Instead of this, there is another variation. So what is that? It's gonna be on second part. Prove that for all n greater than n naught, Pn minus 1 is true. We show Pn. We can do two of them. Instead of just doing Pn plus 1, we can do this one instead. So this is if you have this one, if you have the first one, for every greater than n, Pn is true. We said this is the strike induction. This part, if you show greater than n naught, or if you prove this one, they're gonna call it weak induction. Actually, it's gonna be weak induction. This green one is gonna be weak induction. These two. I will put a star here for both of them. This minor is gonna be weak induction. Does it make sense? Okay. Let's prove something, for example. So let's see. We show the induction. So let's talk about prove this part. Let's show. I want to prove this. I have an example here. Let's prove this example. Show for all n greater than 1 by induction, you say k equal to 1 to n, k squared is going to be n n plus 1 to 2n plus 1 divide by 6. That's what I defined another in the before we go for a break. I showed this one actually. You remember talking about theta and the other one. So we want to prove this one. So this is gonna be P of n, and this is the Strach induction because n is greater than 1. What we need to do? Someone tell me how we do it. Let's just start with just what is this, how it's gonna work, how we are gonna approach this one. Anybody? Yes, we prove the base case. Let's consider, okay, first of all, let me change the color for proof. Actually, I prefer this. Maybe this one for proof. On the proof, we use color. Okay, proof. Okay, how do we do this sum? Let's do the first step. We say P1, we need to show P1 is true. What is the P1 says? Anybody can tell me what is the P1? P1 says, put P1 here, K1 to 1, n is 1 because it's P1, K is squared, it's become, put 1, 2, and 2 plus, it's gonna be 3, divide by 6. What is this one shows? It's gonna be 1 squared, and this is gonna be 2 multiple 3 divided by 6. It's gonna be 1 equal to 1. So we already showed this is true. So base case is true. What should we need to do for the second part? And then we do need to do the induction. Let's do this one. So, okay, I consider, let's do the second part. For all n greater than 1, then we say Pn is true, and we prove Pn plus 1 is true. We say induction hypothesis. So let's show this one. Okay, let's show that Pn is already true, and then show Pn plus 1 is true too. We say, okay, I'm consider for every n greater than 1, we are arbitrary. What we assume for this n that we assume this is true. K equal to 1 to n. K squared is n plus 1 to n plus 1 divided by 6. This is what we said, what we call this one. We call this one a state induction hypothesis. It's a state induction hypothesis. So what we should show, this is what we already have. What we should show we need to show this one because we need to show Pn plus 1 is working. So it's going to be n plus 1 instead of n plus 2, 2n plus 3, because you put n plus 1 here, it's become 2n plus 1 because it's going 2n plus 3, and divide by 6, which we define this part. This part name a state induction conclusion. You assume this one is true and you show this is gonna hold. How we do that? Let's just start. So if I go back, so let's start from what I assume. I assume this one, k from 1, k equal 1 to n plus 1, k squared. So let's show this one. So I need to show this is gonna hold, you know, this part. Let's divide, let's consider this part. Let's break it down. If this is the case, how can I break it down? I can break it down from k to n, k squared, which is gonna be the first part. And then I have n plus 1, which is gonna be n plus 1 squared. I just divide this summation. I bring it out n plus 1. I know if I assume this one is true, based on assumption, this is the result. So this one is going to be n plus 1 to n plus 1 divided by 6. And I know this is n plus 1 divided by 2. This is coming, this part coming from induction hypothesis. Because I know, I got it from that. We consider this is assumed to be true. So, and then what we are gonna do, we just keep going here and prove it. So I just have this one, 6. And then if I do this one, so it's gonna be n plus 1, 2n plus 1, 6n plus 1 squared. Here we put 6 here. N plus 1, we consider doing out. So this is gonna be 2n squared plus n, I think plus 6n plus 6. Am I right? I think that's true. Yeah. So we have 6n plus 1, and this is gonna be 2n squared plus 7n plus 6. Yeah, I think so. Yeah, which is gonna be, this one is gonna be n plus 1. Here we can consider this is gonna be n plus 2 actually, and this is gonna be 2 plus n3. If you multiple this one, it's gonna be 2n squared. Like this one is to 4n, and then 3 and 7n, and this is gonna be 6. Yes, this is the result. And we proved it already. We need to prove this part, and we proved it. So the result is gonna be, result follows of all for all n greater than 1 by induction, it holds. So we just proved this one. Does anybody have any question? Anybody has any question about this? No question at all? Okay, I will write this one, and then you guys start solving this one for yourselves, and I will prove it for next session. Another example, so let x be real and x is not equal to 1. What do you want to show? Show for all n greater than 0, summation of k from 1 to n, xk is xn plus 1 minus 1 divided by x minus